All right, so the topic of chapter 12 is we've got two samples. Like we've got one group of people and another group of people. And we're not really sure if the data that we're collecting on each of them is the same. For example, baby weights. So let's do a different example and practice the same thing. So the idea was, if we weren't sure that these two groups had the same values, the same data, one thing that we could do to test that, our null hypothesis, was, all right, if we think that there could be no difference, then if there is no difference, then the labels that differentiated that data didn't really matter. And so I could have assigned a different label to different people in that data set, like smoker versus non-smoker, and that would give me potentially the same data right back then if they didn't matter. Right? So that's our null hypothesis. That'll be our test. That's what happened. In the population, the distributions of those birth weights, for example, were the same. And so we were able to simulate that, a bunch of different populations with that idea in mind by shuffling labels. And so that's what we did for the last example. And so I want to do a different example, a silly one from maybe not the textbook, but from the Berkeley people. So here is a silly idea. So here is a made-up example from a company called Super Soda. All right, so let's say that the Super Soda people, they run a taste test against their competitor, Coke or Pepsi or whatever, and 91 out of 200 people, they got 200 people that they paid for the survey or whatever, and 91 out of 200 tasters in their blind taste test, they preferred Super Soda over Coke or whatever. Okay, so the question of the higher up administrators at Super Soda, they wanted to know, like, all right, does this mean that we're worse? That's their question, because it's less than 100, right? If it was perfect 50-50 odds, like nobody could tell the difference, right? Maybe the goal is maybe they're trying to copy the Coke formula or something, who knows? But if it was a perfect 50-50 split, you'd think that, all right, 100 out of the 200 would prefer it, and the other 100 would prefer the rival. But it looks like 109 people, they're like, I like the other one better. So the question for the people at Super Soda is like, do fewer people really like Super Soda than the rival? Is the rival really better? Or is this 91 out of 200 just chance, right? Is it like a coin flip, whether this person that we were surveying was going to like it or not? Is going to prefer it or not. Because if that was true, then maybe we could see something like this. Because if you flip a bunch of coins, you flip 200 coins, it's possible that you'll get 91 heads, right? You expect to see about 100 heads if you flip 200 coins, but if it really was 50-50, sometimes you would see 91, maybe. And so that's our question. All right? So that leads to a test, a hypothesis test. All right, so let's try to figure that out. So our null hypothesis, let's try to imagine what that could be, right? It's maybe pause for a second in your mind and think about what kind of null hypothesis could you put here. Yeah, and then in 30 seconds I'll uncover it. But what could we simulate, right? What are we going to assume? What's something that's simulatable that we can maybe get these numbers back with? Remember that null is like null kind of means nothing. So there is no difference. That's going to be your null hypothesis. There was no difference. The people who preferred Super Soda versus the rival, there was no difference in the people who would want one versus another. So it was like the same proportion of people. That could be our null hypothesis. Does that kind of make sense? Questions about that? The same proportion of people prefer the Super Soda versus the rival soda, Coca-Cola or whatever. So if that's your null hypothesis, your alternative is always going to be the opposite of that. If it's not the same, then it must have been different in the direction usually that you cared about. It's like, all right, it must be, the alternative was that fewer people like Super Soda. All right, smaller proportion of people prefer the Super Soda. And then we need to come up with a way to do our hypothesis test, a way to simulate. And I already said what we could do, which is, all right, if it really was the same proportion, then the number of people who said they liked Super Soda in our trial is essentially a coin flip, right? And you count the number of heads or you count the number of tails. Yeah. So that could be our statistic. Like we want to know how many people wanted Super Soda. That's a number that we could come up with, right? Another number would be how many people prefer the rival. That's a different number that's still proportional, right? And just be in a different direction. Another number that you could come up with is like, what is the proportion of people who prefer super soda? So you could do 91 divided by 200. That's another number that you could use here, right? So you have a bunch of statistics that you could choose from, but let's just do number of people because that's similar to like what they did in their original test. Might as well keep it the same. And when we do our test, we're going to get a bunch of different simulated values of how many people like super soda, right? And so we're going to end up with a histogram that looks kind of like this, maybe. We're going to get a big long histogram. Maybe it's got like a peak somewhere. And it's like number of people who preferred super soda, simulated edition. And then our p-value is, all right, these are all the numbers of people who prefer super soda. If we're calculating a p-value, we want to know how often did our simulated idea, assuming that people really didn't like super soda any less than the other one, starting at 91, right? How often did our test, did our simulated environment here, pick the number 91 or something even more extreme that would lead us toward the alternative hypothesis, right? How many times did we predict 91 people like super soda, or 90, or 89, or 88? All those things. Does that kind of make sense? Like, start at 91, wherever it was, maybe right here, and go this direction, kind of. Go left. Does that kind of make sense? That would be the more extreme direction. How many times does your test give you a value of 91 if you're assuming that just as many people like super soda as the other one, as Coke? How many people liked it? How many times did we see 91 people only saying that they liked it, or 90, or 89, or all the way to the left, right? Anything smaller than that would also lead us to conclude that fewer people like super soda. So how often did I see a value that was like this, or even more extreme? That's trying to see how often does this alternative hypothesis maybe appear in our simulated stuff. So yeah, let's try that and see what happens. So I guess I'll use my standard 3 dashes, and then we'll do super soda. All right. So what we really would like to do is we want to have a simulated, I guess, survey of 200 people. A simulated survey of 200 people, and we're assuming that just as many people like super soda as the rival. So I could do sample proportions. I could be like 200 people with a 50-50 split, something like that. And then I could do things like that. Or, that's one way to do it, right? Or I could say, I could flip coins. I could just simulate coin flips, couldn't I? Let's see. That would be np.random.choice on an array of like H and T for heads and tails. Because like if it's 50-50, we'll just count like heads or something. And I want to do this. This just gives me one head or tails, right? Remember how to use random.choice. You could say, give me 200, right? Roll it 200 times, 200 heads or tails, 200 coin flips. And if it really is just a 50-50 split, like I'd see this just equally as often, right? So I'm flipping 200 coins, 200 fair coins, and I'm seeing how often did it land on heads. Let's say that heads means that this sample survey liked super soda. So that's what I want. How often did I see heads here, for example? How often did I see heads? Then I can do np.count non-zero, of course. And it looks like for this simulation, I got 109 people who like super soda. Does that make sense? If it really was a 50-50 split, you could just simulate it as a coin flip. So, all right, in this group of 200 people, it looks like 114 like super soda. This time only 98 like super soda. So you'll see values that fluctuate around 100, usually. But you know that you can get really lucky or unlucky. You could roll all tails if you did this long enough, right? It's just how often is that possible is the question. So the simulations will give that to us. So let's turn this idea into a function. Let's be like, all right, simulate one count for how many people like super soda. And so it's kind of this. And you can change the sample size if you wanted to. So like this was a sample size that we were given. It was 200. So let's say that if you want to up the size, you can change that later. Call it sample size this time. And so now if I call simulate one count with 200 people, now I'm getting how many of those 200 people like super soda. Okay? So this is, again, me simulating this idea under the null hypothesis. If the same proportion of people liked it as the rival soda, then it really is just a coin flip. And here's a simulated group of 200 people with that assumption in mind. And our goal is to see how often does this land on 91 or smaller. Questions about that? See how the simulation is going to work out? So we just want to do this a bunch of times, right? That's the game always. It's all right, let's let the computer handle the problem. Let's say we want 10,000 simulations. We can change that later if we want. And let's just get a bunch of counts. So for I and np.a range, simulations, what do you want to do? Append to your existing counts array, simulate one more count with a group of 200 people, and set that back into counts. That's what we want to do. All right. So I've done this, and it looks like sometimes you see like 106 people like super soda, 94, 96, and so these are a bunch of different values. It got all the way down to 83, interesting enough. And so that's kind of what happened there. And you could turn this into a histogram, right? So are there any questions about what we're about to do, what we're trying to do? We're assuming that the same proportion of people liked super soda as the rival. That's our null hypothesis. That was simulatable. And now we want to calculate a p-value. We want to look at the data, and we also want to calculate a p-value. How often did this simulation, under that assumption, give us a value of 91, which is what we saw in real life with quotes, or smaller, because that would lead us in the direction of the alternative hypothesis. How often does our model predict something that we thought was weird? Because maybe that means it wasn't weird. That's kind of how this works. Okay, so let's do a histogram. I'm just going to copy and paste it. It's faster that way. I made a pretty table, or I made a pretty graph in a cool way. So here, you don't have to understand most of this. So here I put all our counts of heads, because that was super soda in a nutshell, into a table called trials. And then I did a histogram. You don't have to understand what it's doing here, but it's going to color it in, which is going to be really cool. And then we're going to put our number 91 as a little red dot, which is fun. So this is what happened, and this is our simulation. All right. This is our prediction under the null hypothesis. Assuming that that's true, these are all the different values that it took on. These are all the different numbers of people in that size 200 sample group that liked super soda versus over the competitor. And so sometimes if you are assuming that it's an equal amount of people, then it's going to, if it's a 50-50 chance, you're usually going to see around 100, but you'll see stuff around the edges too. And so we saw 91 people in real life who like super soda over the competitor. And our question is, does that mean that it was just chance? All right, so assuming it was just chance, as we are in our simulation, how often do we see a value of 91 or more extreme in the direction that makes us think that people don't like it as much? Under the assumption that just as many people like it, it's this yellow bit. That makes sense. We just kind of want to add up this yellow bit. What's this proportion to the total? Because that's our p-value. That's our graphical p-value. Okay? So that's just us taking our counts and seeing how many times does this take on a value that's equal to 91 or smaller than 91, because that's in the direction that made us think that not as many people must like this thing. But again, we're simulating these counts under the assumption that just as many people like it, right? And everything else is left to chance. So np.count, non-zero. We get all these values, and this number is not very useful unless you divide by how many things you took. So length of the counts is about 12%. So about 12% of the time, our model, under the assumption of the null hypothesis that just as many people like super soda as the competitor, it gave us some values that would lead us to believe that not as many people liked it about 12% of the time, just as it did in real life. Okay? So what does that mean for us? It means that it could have been chance. Right? This is a decent amount of time. It's not like 5% of the time or less. It's 12%-ish. Does that make sense? So that's not too far off. It looks like our null hypothesis can decently often predict this happening. Such a small number. Such a small number. It's not that small, apparently. it was like 70, then there would be a problem. But it looks like this 91 wasn't a big deal. Okay, so yeah, so our conclusion here with our p-value and everything is we're not going to reject the null hypothesis. We would reject it if we saw a value of like 0.5 that would be statistically significant at that point. So conclusion, we do not reject the null hypothesis. And the question is now, that 91 is still like a small number. The question for the people who are trying to make super soda is like, should we improve the formula now? Because like when you're a data scientist, like you have this value, it's like, okay, it's possibly chance, but you don't want to leave things to chance if you can't, if you don't have to. So if you were the manufacturer, if you were the data scientist working at super soda, you'd be like, maybe we should do another trial, right? You do some more, you get some more data just to make sure that that 91 really was chance. Rather than something else that's nefarious. So if you were the manufacturer, you'd probably either like get a bigger sample size, you'd survey more people. You'd probably want to try that, try a bigger sample, just to confirm that it was really random chance, because if you do with more people, these values won't fluctuate as much. I hope you can imagine. All right, bigger sample to confirm that it was just random chance. All right. So yeah, that's the moral of this story. Are there any questions about this little made-up example of soda? Do you see how we solved the problem? How we simulated things? Because that's our testing method in a nutshell. All right. Eventually, towards the end of this, we'll have just a bunch of things for you to try, but I want to, before we do that, I want to talk about all the things that could change this, because we did talk about just now, like sample size. You can imagine that if the sample size was bigger, you wouldn't have as much fluctuation, and then you'd have a better answer. So like maybe pay more people to take the survey. So here's just a list of things that can change what happens when you're doing a test. All right. So quite a few things. Here are all the different, there's probably plenty more where this came from, but let's just talk about, what is this, 5 things? So, all right. The first thing that affects the outcome is what you simulate, right? What you're eventually simulating. So like, what is your null distribution? What is your null hypothesis? And what does that mean for your data? Because you could have been like, all right, it was a perfect 50-50 split. Or you're like, you know what, people were lying. It's more people like super soda. So like maybe it was a 60-40 split, but we still got this bad number. So like that, your null distribution is kind of informing what happens, right? That's changing your hypothesis, okay? Your null hypothesis changes what you're simulating, and you might get a lower value for your p-value or a higher value because of that. So you do have to worry about that. The statistic that you choose as well matters, because we could have chosen different statistics to test here, right? We picked how many people like super soda. We could have also picked how many people like the rival. We could have done a proportion, 91 out of 200. Like what was the proportion of people, the percentage of people who liked the super soda or the rival? So a bunch of different numbers that you could choose, and that those might predict differently, right? Those might give you different numbers. Like how do you measure the difference between your samples? Or a distance that we've done in previous chapters. And then when we're trying to simulate our statistic, assuming that the null hypothesis is true, that the fancy terminology for that is like, we want to calculate an empirical distribution, the one that we're simulating, empirical distribution of our statistic under the null hypothesis assumption. There's that, right? That's going to change things. It's like, how many times do you do your simulation? We did it 10,000 times. If you do it like 100 times, there'll probably be more fluctuation, right? You want to have it settle, so do it enough times. Do it 1,000,000 times if you can. So that'll change your values. That'll cause them to be a bit wonky if you don't do as many things. Of course, the data that you collect matters a whole lot, right? So the age-old question is like, how did you take this sample? Did you call some random phone numbers? Did you interview only people at Clovis Community College? Because that's now biased, right? It's biased towards younger people. It might change, right? You got to think about your demographics. That's important, right? You may be designing a study one day. So yeah, there's that. and you can't get away from the truth either. So like assuming that your hypothesis was, your alternative was true, right? Assuming that really fewer people like super soda, maybe it really was 91 out of 200 really liked it. It wasn't just chance. How far away is that from your null hypothesis? It wasn't that far for us. It wasn't that far for us in this case. All right. So if your difference is not that extreme, it's harder to find the difference, if that makes sense. All right. So those are a lot of issues that could change things. Usually the solution, at least for us in this class, is do things more times in one sense of that word. So what will you increase? All right, so increase something is usually how you solve the problem for Data 8 students right now. So here are the things that you could change. So you could increase the number of your simulations. That's one thing that you could do to make sure that you're simulating that null distribution properly. As big as you can make it is good, right? So make it as big as possible so that your test statistic distribution looks good. And that doesn't mean that keeps you from having to go out and survey more people, which is nice. All right, so that's just let the computer work for a little bit longer. So we did 10,000 simulations. If I did fewer simulations, I would get a weirder looking distribution. I hope you can imagine, because like if you flip 3 coins, you get really crazy things, right? You might get all 3 heads sometimes. If you flip 200 coins, it's really hard to get all 200 heads. That's what I'm trying to say. All right, so if you increase the number of simulations, you'll get a better picture of what your null distribution looks like. That's good. Another good thing that you could do is increase the number of people that you're surveying. That's your number of observations, right? Take a bigger sample, because that will mean that the difference that you see in that bigger sample, it's harder to simulate away. It's harder to leave that just to chance. So a larger sample will let you reject your null hypothesis if it really was true that your alternative was the right one to go with. All right. So yeah, that's the idea there. And so those are the 2 main ways to deal with this right now. Okay. But even these might not be enough one day. So even if you do all this, you do 1 million simulations, you get 2,000 people in your survey, it is possible that the difference from your null distribution is so small that you still don't reject your null hypothesis. So it is possible that it really was 91 out of 200, right? Super soda just wasn't as good. It's just slightly not as good. We didn't notice that because that was close enough to chance. Yeah, that was close enough to chance. So we can't say that it's wrong. We also can't say we can't say that the null hypothesis is wrong. That's what it means. That's why we say we don't reject it. We fail to reject the null hypothesis. We don't say that it's true. We just say that we don't reject it. Do you see the difference there? So that's why that wording is like that. Okay, so even if your null hypothesis is small, but is false, but your truth, right? What is true? Your 91 out of 100 is so similar. It's close enough to the null hypothesis. Then even if you took a large enough sample, you probably won't get enough evidence to reject your null hypothesis. You need a huge sample to notice that it was 91 out of 200 rather than 50-50 chance. So you could solve that, but it would maybe be extreme and it would cost a lot of money and it wouldn't just work out. So yeah, those are some ideas. Those are some things that could go wrong, and that's why we say we do not reject the null hypothesis rather than we accept the null hypothesis as that's what is causing all of this. That's the truth in this situation. So we don't know. I really don't know. All right. Any questions about that? That's a little bit philosophical, but important to think about. All right. And so, yeah, I want to give you some chances to try this out, and I'll give you some head starts. I want you to break open your Jupyter if you don't have it open already, and I'd like you to load in the Titanic data set first, please. So we did this last time. I want you to do the same thing, but with a permutation test. All right. So were women more likely to survive the Titanic? That's something that we did last time, but I want you to try to use a permutation test this time to figure out if this is true or not. All right. Because what do we have in our Titanic data set? It's very similar to this, right? We have some labels of man and woman, don't we? If women weren't more likely to survive the Titanic, because that would be your null hypothesis, right? There's no difference. then it didn't matter if you were a man or a woman telling you who survived. Does that make sense? That's going to be something that you can simulate, right? That's going to be something that you can simulate. And so let's give that a try. And I think that is what I want to do. Yeah, let's do that first, and then I do want to come back to this and maybe give you an example of what I mean. I do have something worked out, but it is a bit long, so I want to have you try first, this Titanic thing. So let me read it in the data set. But try to use a permutation test, just like we did earlier last time. So you can load up our chapter 12 stuff to get that babies and smoking data set example. But here's all this. This is our Titanic data set. If we want to know who survived, like, was it true that women were more likely to survive the Titanic? All we really need to know is, like, for all these passengers, what was their sex and did they survive? So let's call that Titanic.select sex and survive. I'll call that like Titanic 2, like, because that's all you really need, right? And from this, you know, these are all the people on the Titanic. Either they were male or female, or they survived or they did not survive. The question is, like, did more men or more women survive? Were women more likely? That's our question. So your null hypothesis is no. Right? It's going to end up being no. And we're going to simulate that by shuffling labels around. Like, all right, it didn't matter then if you were male or female whether you survived or not. So if you flip these, right? If you flip these around and you shuffle them, assign them back to survived or did not survive, we shouldn't see a difference in the proportion. So let's quickly just do some proportion stuff. So Titanic 2 dot, let's group by sex. And so there were more males than females on the Titanic, it looks like. But if we do np.average to aggregate, survived average of ones and zeros. Average of ones and zeros is a proportion, right? So it looks like 74% of the women on the Titanic survived, and about 19% of the men on the Titanic survived. So that's a big difference, right? That's a big, big difference. And the question now is, what I want you to try is do a permutation test, get these averages after pretending that male and female didn't matter, because that's your alternative, or that's your null hypothesis, right? Women were not more likely to survive the Titanic. So to do this kind of permutation test, where did I define that? We can just shuffle who was male and who was female, assign it back, right? Assign it back to these survives and did not survive, like shuffle all these guys around, just like we did before. And then get these proportions again using those shuffled labels. Does that kind of make sense? Because if it was true then that just as many men as women survived, there was no difference in who survived, then we should see similar values here when you shuffle the labels. Does that make sense? And if you do that a bunch of times with different shufflings, you'll get a good picture of what would have happened on the Titanic if that were true. Because if it was true, we should see the values that happened in real life somehow. That is our goal. So try to look at the code from last time, and at least just do one shuffle. Try to shuffle the labels once. We made it like a new column called shuffle label, I think. Try to get that into this Titanic 2 table, or the original Titanic table, whatever you want to do. And then group by that. Group by your shuffled label and get the average amount of people who survived versus didn't survive for male and female men. See how that changes things. See if it changes things. So I'll give you a little bit to try that. Please ask me questions if you have any. What is this? Interesting. Because it might have been more 50-50. Interesting. I don't know how to get that to go away. All right, so let me remind us how to do that. I'm giving you a head start. So I'm going to work with this Titanic 2 table. If I want to shuffle male and female, I can take a sample, right? Titanic 2.sample, and I'm not sure if I showed this to you, but you want just as many, right? Titanic 2.sample, and I want just as many, right? I want to sample however many people were already on the Titanic. Titanic 2.num rows, right? I'm going to sample, and I want to just shuffle, so I don't want to like clone anybody if I don't have to. So I want to do it with replacement equals false. And so that's one way to do the shuffling, but you don't have to say .num rows if you want just as many. I can't remember if I've shown that to you or not, so I'm going to tell you about it again now. So where is that? .sample. That is a table.sample. By default, if you omit this number, the number of things you want to take a sample of, it gives you back just as many as were in the table. So it samples with the same number, and that's what we want here. All right. So you can omit Titanic 2.num rows. That's the default. It's always the default is the number of rows you had. So I can just call it like this and say Titanic 2.sample with replacement equals false, and it will give me back also 891 rows. Okay, so that's now shuffled all these rows, because originally it was 0, 1, 1, 1, 0, right? It was male and 3 females. So it shuffled them all around, yeah. And I kind of want to take this new shuffling of the sex column, at least. So column sex. And now I've just got a bunch of males and females in a random order, just as many as were there. And I could tack that on to the Titanic 2 table. Does that make sense? So Titanic 2 with a new column we called it shuffled label last time. Take that and put that there. Does that make sense? So now I've reassigned male and female, because that, if we're again assuming that, all right, it didn't matter if you're male or female, whether or not you survived the Titanic, so assign these values now to survive and didn't survive. So it's going to give you a simulated Titanic under in a universe where that's true, where that idea is true, that there really wasn't a difference. Women weren't as likely as men. There was no difference in women being more likely or less likely than men to survive. So that kind of makes sense what we did there. And so if we do a group now on shuffled label, and we do NP to average, take the average of the numeric stuff, do you see how these numbers for, all right, what's the proportion of women and the proportion of men who survived? They're a bit closer to one another than the original values. It's like 75 and 19-ish percent. This is like 40%, is like 38%. Yeah, 39, 38. So that's interesting, right? That's interesting. That is, that's the percentage under the assumption, like of females who survived, under the assumption that women and men were just as likely. That's our null hypothesis. Does that idea make sense? So I want to do this a bunch of times, right? Yeah, so let's try that. So we want to every time we do this, we don't just want this table. We want, let's say that our statistic is what was the proportion of women who survived the Titanic. Under the assumption that it didn't matter if you're male or female, we can do this shuffling and get these values. And the way to get this female survived average here is we could go to its column after we do this grouping, right? This is a table again. This is column 0, 1, 2. Column 2, item 0. Yeah. Column 2, item 0. That would give me the female survival percentage under the assumption that my null hypothesis was true. So simulate the Titanic happening and it not mattering whether you were a man or a woman who survived. These are the proportions that we're getting back when we do that simulation. Does that make sense? That's our null hypothesis. And so we want to do that a bunch. We want to do that a bunch of times, and let's make a function that does that. That's a simulated rate of survival. But give me one simulated rate. That's the kind of terminology we've been using. That's the one that your book likes to use. And so just take all that. Let's kind of do this a little bit backwards. This will give me a table of averages, and then I'll go to that averages table dot column 2 dot item 0 and return that. That'll work. And so that'll do what I want. Give me one simulated rate. That's separate, right? There it is. So this I can do a bunch of times, right? So the question is, this is me assuming that it didn't matter if you're a man or a woman, we were shuffling labels. How often did we get a value this extreme or worse, right? How often did we see this many women surviving, right? Or more, because our alternative is women were more likely to survive, right? So when we're calculating a p-value, it's going to be, all right, how often did our model, under the assumption that it didn't matter if you're a man or a woman, how often did women survive? This often as we saw on the real Titanic, or more, right? Or more, in the direction that would cause us to believe that it wasn't just chance, right? That women were more likely. Because this question is our alternative hypothesis. Does that kind of make sense? That's our alternative hypothesis. And so that's probably worth underlining. That's our alternative hypothesis. Our null hypothesis, then, just to spell it all out for us, is that men and women were equally likely, right? So you could just shuffle the labels and it wouldn't matter. We're equally likely to survive. Okay, and that's what we assumed when that's why we were able to shuffle the labels. Okay, any questions before I do this a bunch of times? Do you see how we got here? Let's see. Yeah, so let's do a bunch of simulations. Let's do 1,000 simulations, because it does take a while to do that resampling. That's the technical term. And so I'm going to simulate a bunch of rates under the assumption that my null hypothesis was true, that there was no difference in men versus women getting saved from the Titanic. So that's why I was able to shuffle those labels. Simulated rates is an empty array for I in np.arange simulations. Oops. What do I want to do? I would like to get a new simulated rate, append that to my simulated rates array so I can keep track of them all, and then assign that right back into simulated rates. Just keep on building up that array. Yeah. And then once that's done, let's just do this all right now. Once that's done, I can put it in a table and make a histogram, right? With a column, give me rates. I'll put my simulated rates there. I can do a histogram on the rates column or column 0. Let's just do like 20 bins or something. And then for a p-value, let's just get this all in one cell for fun. For a p-value, because this part will just draw the graph, and then the last thing that I do will get printed out too. So for a p-value, it's all right. How often did these rates? How often were they as likely as we saw for women in the real Titanic? So how often was it 74.20, whatever that is, 2038% of the time? How often was it that value exactly, or any bigger, right? Because that would be in the direction of our alternative hypothesis, assuming that there were more women who survived than men. How often did we see that? So np.count non-zero, do all that. And then to get a percentage, we divide by the number of things in our simulated rates array, which was the number of simulations. I could have put that there too, but len works just as easily. So that'll take a while because it's got to do a lot of samples. So it's 10,000. 10,000 would take even longer, take 10 times the amount of time that we're waiting for here. But every time we did this, we ran this, it was close to like 40%. We were trying to ask how often was it, like 75%? Let's take a look. So here's our histogram, all right? Assuming that men and women were just as likely to survive, and I could shuffle those labels in, it didn't matter if you're a man or a woman, impacting whether you survived the Titanic. Here are the simulated rates of how often women would survive under that assumption, like down to 32% up to 44%. But in real life, we thought like 75%, right? How often did we see that? In our 1,000 simulations, did it ever come up? Because it will eventually, right? You shuffle it enough times, you'll get back to the original distribution, at least once. We never saw it. It didn't happen. That would be a value, not here, it would be way over here, right? We count how often we got over here or that way, which is never. It's so unlikely. Do it a billion trillion times, eventually you'd get over there, but it's so unlikely that everybody would be populated right here. All right, so that means that we reject, right? That means that we must reject our null hypothesis. Under this assumption, it's so very unlikely, it's actually impossible pretty much to get a value like we saw originally for the number of, for the proportion of women that survived. So that means that our null hypothesis was not a good predictor of what happened in real life, which causes us to reject it in favor of the alternative hypothesis. That one seems more likely. All right. Again, we can't prove anything, but we can say that one sounds better. And here's a number to prove it to you. All right. And here's a number to convince you. You can't say causation, of course, but this is the better hypothesis. Okay. So yeah, that was that test. Are there any questions about it? Does it make sense how we figured all that out? How we shuffled everything? Because I do kind of want to go back just briefly to this idea up here where we're talking about like, okay, these values will look different if we did more simulations or we took a bigger survey. All those things will change what we did, what we see. All right, so I think that's worth talking about. So I've got some things I want to say there. So I'll put it above the Titanic. Let's make some new cells for that. So if we wanted to change the number of simulations, here's kind of what might happen. Changing the number of simulations. All right, and so I've just got a bunch of pre-written code. You don't have to fully understand. I just want to draw some graphs to show you the difference. All right. And so it's going to take a little bit for me to put all this in here, but it's worth it. So let's do it. I'm just going to copy and paste it. Changing the number of simulations. So I've got a big function. Let me just put all this in here real quick, and then I'll explain it. Again, you don't have to understand this code, but it's worth talking about what we see. This is just some simulations that that change different things. Dun, dun, dun. So let's show you that. Boop. And then I want to show you that too. Come back and do. So this is the number of simulations. If you do more or less, different things happen. So let me try running all of these. Some of these will take a second, but okay. Where do I want to be? So this is back to here, right? This is our super soda simulating one count with like originally we did it 10,000 times, right? We did it 10,000 times and we got some values and we got this p-value that's very close to what we had originally. So here I'm doing the same thing. I'm making a function that does our testing and give us a p-value based on the number of simulations. So here I gave it originally 10,000 and the sample size was 200, and we did the same kind of p-value calculation. We got a similar p-value, all right? But if you do that a bunch of times, if you change the number of simulations, right? Here we did 10,000. If you did just 1,000, the value is more fluctuating, right? Here it's now 12. Here it's now 11.7 again. So that's still decent 10. So it's moving around. If I did only 10 or like 100 simulations, I get a wider range of different possibilities, right? I wouldn't be as confident. Sometimes 14% for a p-value, right? Sometimes it might be significant if you did that few, all right? So yeah. Here is an interesting thing, and I just want to explain it to you. So here, what this is doing is it's doing 100 simulations, it's doing 1,000 simulations, it's doing 10,000 simulations of this test all over again for super soda. And it's doing each of those 50 times. So it's doing 50 size 100 simulations, 50 size 1,000 simulations. You don't have to understand this code. And then 50 10,000 size simulations. And it's getting a bunch of different p-values for this number 91 that was important to that test, right? Do you see how the values for when it's 10,000, they're all really close to 11 point something, 2 or 3, right? That one's a bit out of the way. But when it's size 100, I guess you don't see that in this example. But when it's 1,000, the values are kind of more fluctuating. They're a bit more fluctuating. They're going to center around the theoretical p-value, because there is one, because we're simulating around that. But here's kind of a histogram that's showing that. This is all what I want to show you. So if you did only 100 simulations, like you didn't do as many, that's the dark blue, you get p-values way over in this wide range because you can't be as confident. Just like when you're flipping 10 coins, sometimes you do get a lot more heads than tails. But if you flip 100 coins, you're getting more close to 50, right? Getting much more close to 50. This is showing that. Same idea for p-values, all right? When you do only 100 simulations, your values can fluctuate quite widely. When you do more, though, it gets reined in. And once you do a lot, there's eventually a sweet spot that you care about. But 10,000 is a good number, at least for our purposes, like within a decimal place, a couple decimal places. So there's our 10,000 simulations. They're all centered around. It's approaching some theoretical actual p-value. Okay. That's what's happening. And so that's why you want to do more simulations when you can. Does that make sense? That's all I'm trying to say with that. And yeah, again, if you do enough, just like 10,000, do 1,000,000 if you can. They're all going to center so tightly around like a mathematically optimal, perfect actual p-value that was what this was supposed to be. Right? Because a simulation is just based on randomness. There is a tree you can solve for if you take a statistics class, like what the p-value really should be. What is the true one, but we're just simulating that in this class, all right? And so here's another example. This is same idea where we're flipping, this is just a bunch of coin flips. This is flipping 200 coins, just like we were doing in our test. It's essentially what the super soda test was. If you flip the coins, if you do only 100 simulations of flipping 200 coins, the number of heads you see are all crazy. You can do a couple experiments. It looks all wonky between experiments. Like experiment 1, experiment 2. Sometimes for your experiment 2, you saw a lot of heads, just crazy. It happened. So that your distributions look wildly different from one another when your numbers of simulations are small, because fluctuations are easy. Right? You do that again, they look completely different. But when you start increasing your number of simulations, these distributions, if you do it again, you keep redoing your experiments, they start looking closer to each other. So again, it's not perfect because it's random, it's simulated. But when you did 1,000 simulations, you don't have to understand the code other than the 1,000 bit. You do 1,000 simulations and you try to keep track of what happened. The two distributions, like you do 1,000,000 of them, they look closer to one another. All right, they look closer to one another, and they're approaching some theoretical distribution. You do 10,000, they're more or less on top of each other. You see that? So there's less, like they're starting to approach what is a theoretical distribution of like what should happen when you flip 200 coins and you count the number of heads. Does that kind of make sense? That's again just giving you reason to believe that if you can do more simulations, you're going to approach what the theoretical actual optimum is. what the p-value should be, what the distribution really looks like. So the more the better if you can. Throw the computers at the problem. That's what this class is about. So that's what happens if you change the number of simulations. That's very easy for us. As we're simulating things, we can just change a number, wait a little bit longer. The other way to get better values was to survey more people, to get a bigger sample. All right, let's talk about what happens when you do that. Let me copy and paste some things from there, and we'll do that. So changing the size of the this is more expensive, for sure. It was a taste test. But here's kind of how the values can differ if you were to do that. So let me again copy and paste all these. Okay, if I do it that way, there's less weird things that appear. So again, you don't have to understand any of this code. It's just to show you that, all right, here's what happens if you were to change the size of the test. Here's what you would see. Cool, let me run all these. At least for now. That last one will take a while. So you could have done this differently. We could have, like I said at the start, instead of flipping coins, you could have done a call to sample proportions. Like, what was your original distribution? It could have been of how many people like super soda versus the other. It could have been 50-50. That's all this is trying to say. Or it could have been like something different. Maybe it really was not as many people like super soda. We'll try it with a different percentage. But if you do sample proportions with your distribution, like size 200, you're going to get back percentages, right? Of like, okay, this many people like super soda, this many people did not, something like that with your 50-50 split. But if you multiply that by the sample size, you'll get how many people, which is nice. So like 96 people like super soda, 104 people did not like it. 105 people like super soda, 95 people did not like it under these assumptions. Okay, so that's what's happening. And so those are the kinds of values that you'll see. They will fluctuate all over the place. But what if it really wasn't half and half? What if it really wasn't half and half? How many experiments, how many people would you have to survey to notice that? Okay, so here, let's, let me try to explain what this function is doing here. So let's see. If you do 10,000 simulations and your sample size was 200 and it really was a 50-50 split, how often would you assume that super soda was just as good? How often would you assume that super soda, there was no issue with super soda? It's like half of the time, all right? Something like that. Your p-values they're kind of random in this situation because it really is a 50-50 split. Sometimes you get some extreme values, sometimes you get some not so extreme values. Because if it really is a 50-50 split, anything would happen. You could see anything. That's kind of what that means, all right? You'd see different p-values because of that. But let's assume, the last thing I want to say here, this is a bit harder to explain, but it's a good picture if I can get this right. Let's say there is let's say it really wasn't a 50-50 split. Let's say that only 40% of people like super soda versus the competitors. If you rerun this test, you will correctly conclude that a lot more often with really, really small p-values. It's harder to explain, but that's what I'm trying to say here. Your p-values will be much smaller usually. It's easier to notice that because if it really is left to chance, your conclusion is kind of left to chance. All right, your p-values might be large. So let's see here. If there really was a difference in the number of people who like super soda versus the competitor, if it really was not as many people, when you have like small sample sizes, and this is going to take a while again, you will usually still notice that there's a problem, right? Because there is a decently big small proportion, right? There's a decently different proportion of the number of people that like super soda. But if you do larger sample sizes, I think let's just do only 1,000 after that. How often do you see a significant p-value? Pretty much always, if there is a difference. Pretty much always if there is a difference, and that difference was decently far away from your null distribution. If it was like really, I don't know, 49% of people liked super soda and 51% of people didn't like super soda, even with a size 1000 sample size, it's going to be really hard to notice that. So if I run this again, it'll take a while. But look at this, the distribution of p-values. They're all over the place because that was so close to a 50-50 split. It's really hard to notice that it was really 49-51 rather than 50-50. You have to have a bunch of, have like a much larger sample. All right, that's all that I'm trying to say. The p-values will be all over the place. Sometimes you will conclude, okay, yeah, there really is a difference. Sometimes you won't. It's very kind of equally likely to get either. So if there is a large difference in the number of people who liked something versus didn't like something, like in your data set, then the sample size can be small enough, decently small, and you'll easily find that out. But if there is a very, like it was really close to your null hypothesis, if what was really true was really close to your null hypothesis but still slightly different than it, it will be very, very hard to get a sample size large enough to notice that. Okay? That's all I'm trying to say. These graphs are a little bit hard to explain, but I hope that makes a little bit of sense. It's going to be very, very unlikely to notice a difference when your sample size, even when your sample size is large, but the larger your sample size, you will more often notice the difference. Okay? So yeah, the first one's much more easy to explain. Number of simulations, for sure that makes sense, right? Everything starts approaching the same idea. Yeah, once you do that. That one's easy to explain. The other one is important too. Okay? Any questions about that? So that's just proof that you should do both of these things if you can. Spend more computer time, get a bigger sample. That will only improve your outcomes. Okay? So yeah, I think the last things that I want to do is give you some more opportunities to do this kind of thing and practice doing permutation tests. Okay? Any questions before we do that? I just want to go to some other data sets. All right, so let's do that fish diet data set again. Let's do a permutation test, and let's have our question be, scrolling. Let me include that table real quick. Oh, fish. Fish diet.csv. So here's all the people. Let's see all the differences because they're in an order. So here's like a sample of those people. Sometimes it's yeses and nos. There we go. So we got diet. How much fish did these people eat? Do these men eat? And whether or not they got cancer, prostate cancer, I believe, right? So you got a bunch of small, large, moderate, none, I think also is included. And then cancer is just yes or no. And our question is, does not eating fish lead to a higher likelihood of cancer? Because we noticed that, right? We noticed that there were some percentage differences. Let's go remember that, and then I'll have you try a permutation test. Because again, the null hypothesis is going to be, right? Like this is the alternative. The opposite of that would be our null hypothesis. Like there is no difference. It doesn't matter how much fish you ate. Just like getting cancer didn't change whether or not you got cancer. So that means you could shuffle these labels, right? You could shuffle your diet labels and attach them to new cancer values, and you shouldn't see a big difference in the populations. Okay, so yeah, let's remember the numbers at least. So let's do fish. Let's do a pivot table on cancer on the x and diet on the y. And so here's their numbers. How many different diets could you have? It's large, moderate, never, and small amounts of fish. So and then here is cancer amounts. 42 out of 42 plus 507 of large fish eaters got cancer. 209 out of 209 plus 2769 of moderate fish eaters got cancer, and so on and so forth. So to get proportions for these different groups, you could take, essentially, you could take this column, right, for cancer proportion, take the yes column and divide by the totals here, the yes plus the no's. Yeah. So let's do that pivot table. Let's call this pivot table fish 2. And then it's really just like go to the yes column, take that and divide by the sum of the yes column and the no column together. And there's proportions for each of these groups where it goes large, moderate, never, small. And so the never fish eaters, they look to have a bit more cancer more often. Okay? And so that's the number. That's our real life number, our 11.3-ish% of getting cancer. Our question is, was that a fluke, right? Was it really just chance? Like, does not eating fish really lead to that 11.3%? Does it really lead to a higher likelihood of getting cancer? And so that's our question right now. And what I'd like you to do is try to do a permutation test to discover that. Try to do everything that we've done before. Let me, I guess what I could do is I can give you all this code real quick. So if you refresh our chapter 12 page on our code from class from last time, you should see everything that we've done so far today, which is nice. So you've got all this. Get that fish table in here and try to, do you see what you could change, right? This would again be, our alternative hypothesis, right? Not eating fish leads to a higher likelihood of cancer. Our null hypothesis was it doesn't matter. If you eat fish or don't eat fish, everybody gets the same rate of cancer. Which implies, right, to do a permutation test, that means you didn't matter what your diet was, shuffle those, right? So try to shuffle that table, shuffle the diet column, and then attach it back to the table. Attach it back to the table, give it new yes or no's for cancer, where the diet didn't matter. Does that kind of make sense? To do that, shuffling and reattaching, and then again try to get those percentages. Try to get the percentage of the nevers getting cancer, right? Percentage of the nevers getting cancer, because you want to see how often that assumption, right, our null hypothesis distribution predicts what we saw in real life. Do we see 11.3% again? How often does that happen for our nevers? Because that was the category that we cared about. You see that? So try to do that shuffling, reattaching, and then getting the proportion for the never fish eaters, because it's new people that you've labeled never now because you've shuffled things. How does it compare? Does that idea make sense? Let me know if you have any questions. I'll give you a couple minutes head start there. Again, our alternative hypothesis is that not eating fish leads to a higher likelihood of cancer, which implies that our null hypothesis is the opposite. It's like, no, there is no difference. So it didn't matter how much fish you ate, which means that diet column was irrelevant. It could have happened to anybody. Okay, let me show you my thoughts here. So it's going to be very similar to the other examples, but I want to take this table, this fish table, and I want to shuffle stuff. So I want to, how do I shuffle these diet labels? You say dot sample, and then if you want just as many things, you don't have to give a number, you just want as many things, but you don't want to duplicate anything, don't want to clone anybody, you want to just shuffle the existing labels, so you always want to sample without replacement. So with replacement equals false, and if you just say that without a number, it'll give you back just as many things, but it's now shuffled the labels, or it shuffled all the rows. So you can take out the diet column of this shuffled table, I'll just call it column 0 because it's the first one, and now I've got an array of smalls and moderates and nevers and things. And that can go and be my shuffle table. So take the original table, add a column. With a column, I've called it shuffled label this whole time. That's all those. And that's what you get. So now I've taken the original table and I've shuffled all the labels and I've assigned new labels to each of those people. Does that make sense? You do it again, you get a different shuffling. That's, again, us assuming that it didn't really matter. It didn't really matter how much fish you ate, whether or not you got cancer. So let's call that shuffled table or something. Give it a name. Because we're going to do this bunch. Right? We're going to put this in a function. And then we want to get these percentages for nevers now and see how it compares to this 11.3 that we saw in real life. Because if we do see 11.3 enough times, then doing this, it meant that it really didn't matter, right? So, yeah, taking this shuffled table, how often, who are the nevers? Just go to the nevers only. Do a dot where the shuffled label. That's the new assignment of how much fish these simulated people eat. So here's the original nevers. All right, sorry, now. Sometimes they were part of the original group, but sometimes they're part of a different group. Here, they are nevers now, though. All right, they're nevers now, and we want to see their cancer rate. So count the yeses out of all of these, okay? So let's call this the never table. And so taking that never table and counting how many times we saw cancer, the cancer column. It's another way of doing what we did, right? We just care about the nevers at this point. So give me the cancer column. It's got a bunch of yeses and nos. How often was it yes? np.count non-zero, right? After comparing, how often was it? It was 10 times for this sample, for this simulation. And the proportion is divide by the number of rows. This is like 0.8%, or sorry, just 8%. It's like that's a simulated never group. All right. And then we want to do this a bunch of times. So I think it's worth pausing. We have a little bit of time. Let's try to do the same thing. Try to make a function called, we're getting cancer rates here. So try to do a function called one simulated rate that does all this. You see how you put these ideas? Because you want to do this again and again and again and get a number like this. I'll give you a couple minutes to try that because we want to call this function a bunch of times and see if it sometimes gives me like 11.3, because that would mean that, okay, maybe it really didn't matter. That's concerning. Yeah, let's try it. For me, it's as simple as kind of copying and pasting, but you probably had to type it. So here, there's my shuffle table. And then I want to go into that, get the nevers out, and give back this value that we've calculated here, which will be a return. I always want to give it back with a return now. That's how the functions work. If I call this a bunch of times, now I get different values, one simulated rate, all right? And so, yeah, let's just do a bunch of simulations again. Maybe we can do it in the same way because we've also called it one simulated rate for the other one. It was survival rate last time. But this is again called one simulated rate, so I think I can keep everything the same here, except for the p-value calculation, right? The p-value calculation was how often in our rates was it equal to this 11.3% for the nevers that we saw in real life, or even more extreme, right? A value that would be even bigger. It's like, all right, that there was a real difference and people got cancer more often, higher likelihood. That was our alternative direction. So again, I'm only doing 1,000 simulations because it is a bit of an intensive process. So we were doing like 10,000 for the coin flips and things, but it's taken a while just to do 1,000 here for this one because it's got to shuffle almost 1,000 rows for every simulation. And that does take a little while. Question? Yeah.
What's the 0.11290?
This was our cancer rate for the never fish eaters. Where was that? It was 14 over 14 plus 110. That was this percentage. Because we saw that for the other people, for the large and the moderates and the smalls, about like 7.5% getting cancer. This one was the one that jumped out to us. So that's why we're doing this simulation. That's why we're asking the question. Yeah. Like how often did we see this value or something more extreme? So our simulation is predicting this. It's not perfect because I used too many bins probably, but here are the rates for getting cancer under the assumption that it didn't matter how much fish you ate. Here were the simulated never fish eaters in this situation. How often did they get cancer? As not often as 2%, up to like 15% of the time they got cancer in our simulated world. And our question is, how often did we see like 11.3%, like here-ish, or bigger, because this would be like extreme. These are the extremes that we saw in real life in the actual study. Like how often does our model, under the assumption that it didn't matter, predict that the nevers got cancer? How often does our model predict what we saw in real life? It looks like 4% of the time, which is not a lot. That's less than 5, so this is statistically significant. And so that would lead us to, just like we did last time, we will reject the null hypothesis. It is not very often, it's less than a 20th of the time, right? Less than a 25th of the time. It is not very often that our model, that our empirical distribution under the null hypothesis gives us a value that we saw in real life. It was not very often. It predicts it sometimes, but not usually. And so that probably means that what we saw in real life was abnormal. It wasn't just chance. And so we can conclude that it's our alternative hypothesis is a better description of the data that we see. Again, we cannot prove causality unless we design the study in a special way. And they did. They used twins, I think. And so we can't actually prove causality here, which is fun to think about. So that points us in the direction that, if you don't eat fish, you will likely get cancer, get prostate cancer as a man. You're more likely to, at least. Doesn't mean you will, but you are more likely to. And that is legitimate causation because of the way that they designed this study. All right? That's pretty cool to think about. Yeah, I think that's all that I want to say. Any questions about how we found this? All right, you kind of get the idea now, I hope, of how we play this game. Let me give you this code too, just in case you need it. So I want you to try one more. I'll pause some more so that you can try it, because you're kind of getting the idea now. So let's go back to, for our last example that I want you to try out, let's do the serial data set. So let me read in that serial data set. here are all the cereals, and we notice that shelf 2, right? Shelf 2 is very, very sugary. So let's remember all that. So cereal dot, let's select out just the shelf and the sugars. That's all the shelf that the cereal was on, how many grams of sugar that cereal had. And if we group that by the shelf column and we do an average, it'll give us the average sugar. Right? So it looks like the shelf 2 cereals had quite a lot more sugar than the other ones. All right, so that was the shelf at like the eye level of a toddler, apparently. So with that in mind, this is a simpler table, right? Let's call this like let's call that cereal 2. Maybe that's what we can use. So there's that. Do you see how you could turn this into a permutation test? We are asking the question, were cereals on shelf 2 selected to be extra sugary? So that becomes our alternative hypothesis. Do you see what our null hypothesis would be? Can somebody give it to me?
If they were random or not.
Yeah, they were just randomly selected off the back of the truck. Good. It didn't matter. It was just completely random. Hypothesis. The shelf 2 cereals were selected randomly. And so, do you see what that implies about the sugar content of those random cereals? It was just like, it was high due to chance, because of complete random chance, all right? And sugar was high due to chance. What's the right word here? Just by chance. By chance alone, let's say. Something like that. Does that make sense? And that's what you can simulate. Do you see how you could use a permutation test to simulate that? With this kind of table, what could you shuffle? How could you make new shelf 2s? You kind of see it? I guess you could shuffle either of them, but the way that we've been doing is it's the label that describes them is the thing that we could shuffle, right? So if it didn't matter, if we just randomly got some sugary cereals on shelf 2, then it doesn't actually matter what shelf the cereal is on, right? It doesn't actually matter what shelf the cereal is on. If I shuffle these, then I should see sugary cereals on the shuffled shelf 2. Yeah, that's some alliteration in that sentence for sure. If you do that, you shuffle these shelves, you'll have some new shelf 2 cereals, right? It's a permutation test, but it's similar to the way that we did it before. It's just with a new idea. We should see similar amounts of sugariness sometimes. Yeah, we should see this 9.62 or even worse appear. If it really was just random, then this shouldn't be too unlikely, right? This shouldn't be too unlikely to randomly get. And that's how we simulate, okay? Assume the null hypothesis was true. Therefore, go and shuffle these labels, get new shelf 2 cereals, figure out how sugary they were. That's one simulation. Does that make sense? Questions about that? Because that's all you got to do, right? Do that a bunch of times in a function, and then you're good, right? You have an array then of sugary amounts for random shelf 2s. Go and do a histogram, go and get a p-value by comparing it to this 9.61 or 9.61905. See how often you got a value that was like that or even more extreme, because that'll tell you if our null hypothesis was a good predictor of the data. Because if it wasn't, our p-value will be small. It was unlikely to see that. And that would cause us to reject the null hypothesis. All right, so I hope you see how this game is being played. It's always the same strategy once you get it down. Okay, so try to do the whole thing. I'll give you a few minutes to just try it, ask questions as you're doing it. But do you see how you might get all this? Read in the cereals table, do that shuffling. I'm giving you all this code from before. Do the shuffling, attach the new shuffled labels. Pick out the shelf 2 of the shuffled labels, right? Because those are the new ones. Pick out those shelf 2s and get the averages with a group, right? Because if you do that kind of grouping like we did there, you could go to what? How would you get that value? It would be column one's item one. That would give you what you need. For this one, because the data set is so small, you can probably get away with 10,000 simulations. We did only 1,000 for the other ones because there's like 1,000 rows. This one only has like 50 rows. And so it's easier to shuffle. I'll give you another minute head start. So I hope you kind of see the pattern here. What we like is, I'll use this serial 2 table because it's a little bit shorter. I want to shuffle the shelf. So I want to take then a sample of the whole table without replacement, because that would give me a new arrangement of these rows. And then I just want to take the shelf column out of that, because that will give me column shelf. That will give me a new arrangement of these shelves. If I do this again, I get a different order, right? Different order, different order. This time it goes 1, 2, 1 instead of 3. And then I want to tack these back onto the original table. So I'll call this serial, I'll just say serial 2 with column, right? Go to call it shuffled label like we've been. But of course you can call it anything. And you put that there. So there it is, right? Now I've got a new shelf for these serials. We're randomly picking new ones, and this is the way we're doing it with this permutation test. And then all I really want to do is get the average amount of sugars for the shelf 2s in the shuffled label. So one thing I could do is let's select out just the shuffled label and the sugars, because when you do an average by grouping, it will average together anything that's numeric. And so we're using these shelves as categorical things, but also they're numbers. And so if I don't do this, it'll look a little weird. Let's select out the shuffle label column and the sugars column. That's 2 and 1 in that order. It's now just shuffled label and sugars. And then if I do a group by the shuffled label column, which is just column 0 in this count, in this idea, and then do average, then it should be happy. So here's shuffled label. Okay, here's the new shelf 2. If I want to get its amount of sugars, it's going to be what? Column 0, 1, item 0, 1. Yeah. Column 1, item 1 gets me shelf 2 stuff. Column 1, item 1. So there's the random amount of shelf 2 sugar content for my shuffled label selection of shelf 2. If I do this again, I get different amounts of sugar. Does that make sense? There's a lot of things together. You see the progression? And so then we can turn this into a, because we like to, we turn this into a function that just does this very quickly for us. So it'll look a little bit ugly because I did this all in one line. Call it 1 simulated average amount of sugar. So 1 simulated average. And I'll just return whatever this did, right? Return all this, please. This number that this big, long Python expression gives back to me. And so if I call it 1 simulated average, we get a number, right? You do this a bunch of times, and you're good to go. Let's do, let me just copy and paste all this all over again, because that is easier for me. So instead of doing it once, let's do it a bunch of times. And so it's not simulated rates anymore, it's simulated averages. Averages, 1 simulated average. Simulated averages. Simulated averages, simulated averages. And then how to calculate the p-value, what's the number that we care about with these values? Let's make sure I've changed it all in the right spots. The number of simulations, we can do 10,000 this time because it's a small table. Yeah, that should work. These are now called averages, not rates. That seems right. And so, okay, to calculate a p-value, we want to know how often do these averages give us something as extreme as the original shelf 2, this 9.61. How often was it that? So how often was it equal to that? Or any more extreme, right? Because our alternative was that shelf 2 was more sugary. So how often did we see a value that was like this or even more extreme in the direction of the alternative hypothesis, so greater than or equal to, okay? And so if we do this, it'll take a little bit because 10,000 is still a big number for table shufflings. But let's see what happens. And we'll get back a p-value as well as a histogram. Nice. So here it is. When we shuffle these shelf labels, we get new assignments for shelf 2 for serials. And here is the distribution of the average sugar content on those randomly selected shelf twos under the assumption that the null hypothesis was true, which was that it didn't matter, like the shelves were just chosen randomly for the cereals. So it looks like they're like the most populous one is about 7 grams of sugar for a random shelf twos. But sometimes you get not as many, like you get all the healthy cereals chosen for shelf two. Sometimes you do get some decently unhealthy cereals, and we're looking for like 9.6, which is like over here. Often, what did our model predict? 9.6 or even more extreme. So it's just a little sliver. See that? Just a little tiny sliver. And it's not very often. Our model gives us a shelf that was this sugary 0.05% of the time. See that? Not 5%, 0.05% of the time. That's practically never. So it's so unlikely that this model that assumes random selection of cereals predicts the shelf 2 that we saw in real life. And so our conclusion then is we reject the null hypothesis. We reject it. It does not predict the data properly, nearly well enough. It's so unlikely that this really happened. We'd be in, what, 5 out of 10,000 universes. That's not right? It's very, very unlikely that we are there. So it's more likely then that we're over here, that the sugary cereals were placed on shelf 2 deliberately, and that is our conclusion. We can't prove causation again, but we can say we reject the null hypothesis. It is extremely statistically significant, the difference that we saw here. It's virtually impossible for this to happen randomly. Okay, so that is the conclusion, and yeah, that leads us to have faith in the alternative hypothesis over the null, and so we say we reject the null hypothesis because of that. Okay, any questions about this process? Do you see it? See it working out? It takes some fiddling to get like the piece that you want, because we have to again come up with what is our statistic, right? Our statistic ended up being average sugar. And then how did we simulate and get that every time? That was a little complicated. But once you find that number, you can do it a bunch of times, right? You can do it a bunch of times and compare it to the originals. So yeah, I think that's what I wanted to say. So in a permutation test, you're shuffling things. It shouldn't matter your label, so go and not let it matter. Go and shuffle it around, see what happens. And I think that's all that I wanted to say. Are there any questions about this example or anything else? Because I think that's the end. That'll bring us to the end of these slides. All right, if we're good, the last thing that I want to do is assign due dates for homework 7 and lab 7 in that order. And that will be it. So let's go do that. Homework 7, lab 7, and then let's look at when existing things are due. So I always like to give you at least a week, right? At least a week. So we've also got spring break. We've also got spring break coming up, right? Spring break is next week, right? I think so. Spring break is next week. So let's say, I don't really want to make anything due spring break. So I don't know, I'll give you more time then. So let's say, yeah. So not the week of the 1st, 2nd, 3rd, and 4th, the one after that. So if that's that one, I need my other calendar for this. We've got nothing due anyway. So let's skip spring break and let's say the Wednesday of week 12, which is 2 weeks from now, even though this is currently week 11 because of spring break. Let's do, so the 8th of April for homework 7, right? The 8th for homework 7, and then the 10th, the Friday, for the lab. So April 8th for that one. And April, what was it, 10th? Yeah, April 10th, the Friday for that one. And I think that's all. So nothing due during spring break, that would be evil. And I think that's all that I wanted to set. Any last questions that we want to keep on the recording?